When traditional software breaks, IT teams rely on standard runbooks to bring it back online, but those playbooks are useless for deployed artificial intelligence systems. Standard code is deterministic. It fails loudly. If an error occurs, the software crashes, throws an exception, or times out, resulting in a clear binary state. The system is either up or down. This flowchart shows the operational difference. On the left, deterministic execution ends in a hard crash. But on the right, machine learning models fail silently. The system stays green and keeps running, even as its outputs degrade into harmful territory. This silent degradation is driven by concept drift. Over time, the real-world data the model processes diverges from the data it was trained on, causing its mathematical weights to skew unnoticed. This vulnerability invites adversarial manipulation. In a data poisoning attack, malicious inputs bypass standard firewalls because the pockets look identical to valid training data. They enter the pipeline and quietly rewrite the model's logic from the inside. Standard Security Operations Center monitoring tools are calibrated to find malware signatures and network spikes. They cannot detect these probabilistic anomalies. Because artificial intelligence is mathematically stochastic, treating it like standard software guarantees blind spots. Integrating it into production requires a mathematically aware incident response strategy. Building that strategy is no longer a best practice. It is a formalized regulatory requirement. The mandate comes from version 2 of the Hong Kong Code of Practice for AI Systems Engineers, which aligns local governance with global technical benchmarks. Specifically, the code maps its requirements directly to the manage function of the NIST AI Risk Management Framework 1.0. This creates the baseline for a 1.0 incident response plan. Crucially, the code demands explicit sign-off from an individual engineer rather than relying on a corporate policy approval alone. If a deployed model degrades and you lack this documented plan, both the organization and the engineer who signed off face severe professional liability. When machine learning models operate in physical environments like the Cross Harbor Tunnel, they are subject to strict zero-tolerance failure conditions. The trigger dictating when a mandatory incident response plan is required is defined by a 4-tier risk framework, adapted from the EU AI Act and Hong Kong's medical device standards. This table illustrates the tiering system. At the bottom, tiers 4 and 3 cover minimal and moderate impact systems. These don't require a formalized plan. Moving to tier 2, high-impact public interest systems. Failure here disrupts essential public services. This classification captures algorithms used for credit scoring and software determining eligibility for essential services. Finally, Tier 1 captures critical safety systems. Here, a malfunction can cause loss of life, physical injury, or the disruption of democratic processes. Medical diagnostic AI and the critical infrastructure monitoring networks governed by the Computer Systems Ordinance fall directly into this category. For any architecture classified as Tier 1 or Tier 2, a completed 1.0 incident response plan is a hard legal prerequisite before deployment. By enforcing these classifications, risk tiering turns the response plan into a mandatory operational gatekeeper for all high-stakes engineering. This schematic outlines the required blueprint of the 1.0 response plan, mandated by Section A8 of the Code. It operates across 4 primary quadrants. The first pillar is detection. Engineers must design and implement continuous monitoring loops specifically calibrated to identify statistical output anomalies. These loops must be sensitive enough to immediately flag suspected personal data breaches or unauthorized hallucinations from generative models. Once an anomaly is detected, the system moves to Pillar 2, containment. The plan requires pre-programmed isolation protocols executing the moment a risk threshold is breached. Under Section A6 of the Code, these protocols must include automated fail-safe mechanisms and immediate hard power shutdown procedures. The objective is to rapidly decouple the unpredictable stochastic machine learning model from the rest of the deterministic production environment. This isolation prevents the AI anomaly from triggering a catastrophic crash across the broader public service infrastructure. The third pillar is notification. This is where the engineering framework interacts directly with statutory law. The clock starts the moment an anomaly is detected. The first strict timeline the engineer must manage is a 72-hour window. Any suspected data breach or abnormal output must be escalated to the Privacy Commissioner's AI Security Hotline before this 72-hour window closes. If the failure involves a Tier 1 safety incident, a second statutory clock begins, the 5-working-day window. Within 5 days, the team must submit a preliminary root cause assessment to the registration committee. Only after reporting can the team move to the fourth pillar, remediation. This phase requires executing pre-verified rollback safeguards, which are heavily scrutinized for systems equipped with continuous learning capabilities. These rollback procedures must be as rigorous as the controls established by the Department of Health's Technical Reference for AI Medical Devices. These reporting clocks and recovery protocols establish the response plan as a legally binding compliance instrument. It is easy to assume that governing these models is strictly a corporate responsibility, handled by organizational policy. At the macro level, it is. Organizations manage this through standards like the ISO 42001 AI management system. But the version 2 code creates a precise bridge between that high-level corporate certification and the ground-level reality of engineering execution. It defines the role of the responsible AI systems engineer. This professional must personally sign off on the incident response architecture for Tier 1 or Tier 2 deployments. The stakes are high. If a safety failure reveals gross negligence, the engineer faces immediate disciplinary action, including suspension or revocation of their registration. The 1.0 AI Incident Response Plan is the definitive interface between unpredictable machine learning code, strict regulatory oversight, and individual professional accountability.